Both Aristotle and Newton believed in absolute time. That is, they believed that one could unambiguously, unambiguously measure the interval of time between two events, and that this time would be the same however measured. Afraid they used a good clock. Time was completely separate from and independent of space. This is what most people would separate from and independence of space. This is what most people would take to be the common sense view. However, we have had to change our ideas about space and time, although our apparently common sense notion work well when dealing with things like apples or planets that travel comparatively slowly. They don't work at all for things moving at or near the speed of light. The fact that the fact the fact the fact that light travel at a finite but very high speed was first discovered in 1676 by the Danish astronomer Ole Christensen Romer. He observed that the times at which the moons of Jupiter appeared to pass behind Jupiter were not evenly spaced, evenly,
Evenly. Evenly.
evenly, evenly spaced, as one would expect if the moon went round Jupiter at a constant rate. As the Earth and Jupiter orbit around the Sun, the distance between them varies. Distance,
Distance.
distance, distance,
Distance.
distance, distance between them varies, varies,
Varies.
varies. The distance between them varies. Romer noticed that eclipse of Jupiter moons appeared later the farther we were from Jupiter. Eclipse.
Eclipses.
Eclipses. Romer noticed that eclipses of Jupiter moons appeared later the farther we were from Jupiter. Appeared.
Appeared.
Appeared. Appeared. Later.
Later.
Later. Appeared later the farther. Farther.
Farther.
Farther. Appear later the farther we were from Jupiter. He argued that this was because the light from the moons took longer to reach us when we were farther away. Argued.
Argued.
Argued. He argued that this was because the light from the moons took longer to reach us when we were farther away. His measurements of the variation in the distance of the Earth from Jupiter were, however, not very accurate. Measurement,
Measurements.
measurement, measurement,
Measurements.
measurement,
Measurements.
measurement,
Measurements.
measurement, measurement,
Measurements.
measurement, measurements,
Measurements.
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 Measurements. Measurements. His measurements of the variation of the distance of the Earth from Jupiter were, however, not very accurate, and so his value for the speed of light was 1. Okay.
40,000.
No.
40,000.
40,000. What?
140,000.
140,000 miles per second. Second. Compared to the modern value of 186,000 miles per second. Nevertheless, Romer's achievement in not only proving is not only proving that light travels at a finite speed,
finite,
at a finite speed, but also in measuring that speed.
measuring,
Okay, good. Measuring that speed was remarkable.
remarkable,
Remarkable. Coming as it did 11 years before Newton's publication of Principia Mathematica.
Principia Mathematica,
Principia Mathematica. A proper theory of the propagation of light didn't come until 1865, when the British physicist James Clerk Maxwell,
physicist,
the British physicist James Clerk Maxwell succeeded in unearthing the partial theories that up to then had been used to describe the force of electricity and magnetism. Maxwell's equation predicted
equations,
predicted that there could be wave-like disturbance.
magnetism,
What?
disturbances,
wave-like disturbances in the combined electromagnetic field, and that these would travel at a fixed speed, like ripples on a pond, if the wavelength of this
wavelength,
wavelength of this
these,
This wave, the distance between one wave crest,
crest,
and the next, is a meter or more. They are what we now call radio wave. Shorter wavelengths are known as microwave, a few centimeters, or infrared, more than a 10,000th of centimeter. Visible light has wavelength of between only 40 and 80 millionths of centimeter. Even shorter wavelengths are known as ultraviolet, X-rays, and gamma rays. Or maybe rays,
rays,
rays. Maxwell theory predicted that radio or light wave should travel at a certain fixed speed, but Newton theory had got rid of the idea of the absolute rest. So if light was supposed supposed
supposed,
supposed 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 to travel at a fixed speed, one would have to say what that fixed speed was to be measured relative to,
measured,
measured to be measured relative to. It was therefore suggest that were there was a substance called the ether that was present everywhere, even in empty space. Light wave salt that was present, oh, I'm sorry, likewise salt traveled through the ether as sound wave traveled through air.
air,
Air through air, and their speed should therefore be relative to the ether. What is ether? Ether.
ether,
Ether, and their speed should therefore be relative to the ether. Different observers observers moving relative to the ether would see light coming towards them at different speed, but light's speed relative to the ether would remain fixed. In particular, as the Earth was moving through the ether on its orbit around the Sun, the speed of light measured in the direction of the Earth's motion through the ether when we were moving toward the source of the light should be higher than the speed of light at right angles to that motion. When we are not moving toward the source, in 1887, Albert Michelson, who later became the first American to receive a Nobel Prize for Physics, prize,
prize,
prize, and Edward Morley carried out a very careful experiment at the Cass School of Applied Science in Sheffield. Applied, applied,
applied,
applied. They compared the speed of light in the direction of the Earth's motion that with that at right angles to the Earth's motion. Maybe back.
Earth's,
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 Earth's. To their great surprise, they found they were actually the same,
exactly,
exactly were they found they were exactly the same. Between 1087 and 1905. Oh my god.
1887,
1887.
1887,
Okay, nice. Most notably, not notably, what
notably,
notably, notably, notably by the Dutch physicist, Hendrik Lorentz,
physicist,
physicist, to explain the results, the result of the Michelson-Morley experiment in terms of object contracting and clock slowing down when they move through the ether. Contracting,
contracting,
contracting, and clocks slowing down when they move through the ether. However, in a famous paper in 1905,
1905,
oh, 1905, hitherto unknown critic in the Swiss patent office, Albert Einstein, pointed, pointed or point,
pointed,
okay, pointed out that the whole idea of an ether was unnecessary, providing one was willing to abandon the idea of absolute time. A similar point was made of a similar point was made a few weeks later by a leading French mathematician, Henri Poincaré. Einstein's arguments were closer to physics than those of Poincaré, who regard this problem as mathematical.
regarded,
Regarded this problem as mathematical. Einstein is usually given the credit for the new theory, but Poincaré is remembered by having his name attached to an important part of it.
attached,
Atta- attached,
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 attached, attached to an important part of it. The fundamental postulate of the theory of relativity, as it was called.
postulate,
Postulate of the theory of relativity.
relativity,
Relativity as it was called, was that the laws of science should be the same for all freely moving observers, no matter what their speed.
matter,
matter, no matter what their speed. This was true for Newton's laws of motion. But now the idea was extended to include Maxwell's theory and the speed of light. All observers should measure the same speed of light, no matter, no matter, no matter how fast they are moving. This simple idea was some remarkable consequences. Oh, I'm sorry.
remarkable,
Remarkable consequences, perhaps the best known, are the equivalence of mass and energy summed up in the Einstein famous equation E E is
E equals mc 2,
or equals here. E equals mc quadrat, where E is energy, m is mass, and c is the speed of light. Okay,
m,
m. And the law that nothing may travel faster than the speed of light, because it's like
light,
light, because of the equivalence of energy and mass. And mass is
mass,
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 mass, the energy which an object has due to its motion will add to its mass. In other words, it will make it harder to increase its speed. This effect is only really significant for objects moving at speeds close to the speed of light. For example, at 10% of the speed of light, an object's mass is only 0.5% more than normal, while at 90% of the speed of light it will be more than twice its normal mass. As an object approaches the speed of light, approaches
approaches,
approaches is it its mass raises ever more quickly, so it takes more and more energy to speed it up further. Further,
further,
further. It can in fact never reach the speed of light because by then its mass will have become infinite. Infinite.
infinite,
Infinite. And by the equivalence of mass and energy, it will have taken an infinite amount of energy to get it there. For this reason, any normal object is forever confined by relativity to move at speeds slower than the speed of light. Only light or other waves that have no intrinsic mass and move can move at the speed of light.
intrinsic,
Intrinsic or other wave or
waves,
wave,
waves,
wave, waves,
waves, waves,
waves, waves,
waves, waves,
waves,
waves,
ways,
waves,
ways. An equally remarkable consequence of relativity is the way it has revolutionized,
revolutionized,
revolutionized an equal remarkable consequence of relativity is the way it has revolutionized of our ideas of space and time. In Newton's theory, if a pulse of light is sent from one place to another, different observers would agree on the time that the journey took.
observers,
Observers would agree on the time that the journey took. Science time is absolute, but will not always agree on how far light traveled. Science space is not absolute. Science since I'm sorry
since,
since the speed of light is just the distance it has traveled divided by the time it has taken. This is
divided,
divided by the time it has taken. Different observers would measure different speed for the light. In relativity, on the other hand, all observers must agree on how fast light travels. They still, however, do not agree on the distance of the light has traveled by, so they must therefore now also disagree over the time it has taken. The time taken is the distance of the light has traveled, which the observers do not agree on, divided by the light's speed, which they do agree on. In other words, the theory of relativity put an end to the idea of absolute time. It appeared, it appeared,
appeared,
appears that each observer must have his own measure, measure of time. Okay.
measure,
As recorded by a clock carried with him, and that identical clock carried by different observers will not necessarily agree.